we'll come back to the survival analysis and reliability. And Tuesday, I explained what is normal distribution. Of course, you guys should know this function, this expressions, okay? X minus mean divided by standard deviations, take the square. This thing is called z-score square. And once you have a z-score square, split it half and take the exponential and normalize, standardize by this standard deviation and square root of 2 pi, and you will have your normal distribution. But you know, mathematicians figure out how to integrate the things, and if you remember in your stat 101 or 10, no, in your stat, that function actually cannot be integrated directly. You have to take the square to do it. So this is not an easy function to deal with. Luckily, this is widely used, so Excel got the normal distribution, normal inverse, everything's, okay? And so what you need to remember is before you plug into the Excel to get this function value or figure out how high is the bell shape, what is important is where that bell shape coming from, okay? The bell shape is really coming from the power of average, okay? And I don't want to, spend too much time on that one, and I want to get to the next topic, distribution. That was the reason I talk about normal distribution is normal if I take the log of something, and I have a survival time or something. Once I take the log of that things become normal, okay? And I explain log in many classes, okay? In my world, log can do 3 things, okay? The first thing is an inverse function of exponential. So if you have something grow exponentially, you take the log, it coming bent down. So in other words, is that it's a way to linearize exponential growth function. The second thing is that in statistics, okay, you basically said that if I have a regression is supposed to have a lot of variation in the same bandwidth, the same amount of variation. If you see the things like a trumpet shape, and imagine you have a set of data look like a trumpet shape, means what? The magnitude increase, and then the variation increase. Can you guys see that? Visualize that. If you have a constant variation, when the magnitude increase, the values is constant, then you can use a regression directly. But if you start seeing a trumpet shape, that means what? When things go up, the variations increase with it. And now you violate the equal error variations term in your regression analysis or least square analysis. So you need to take a log to make sure that they are straight. And the third one actually is similar to that, is in in human factor, I talk about this a lot, is that human, when we evaluate things in different scale, and a lot of time, if you see that the magnitude of your judgment is scale dependent, then you will take the log. So the mathematical way to think about this is d log x dx equal to what? 1 over x, right? So d log x equal to dx over x. So in other words, x increase, the dx go with it on the judgment, and you will do you will use log. Okay, so those are 3 common use in human factor, in regression, and in mathematics. And in this class, log play a major role, okay? And you're gonna hear me talk about log a lot, is because a lot of distributions looks ugly. Means that got a heavy tail, got a long stretch, and whenever you see a long stretch, I want to pull the tail back in to make them look normal. How to do that? Take one log to make sure that everything looks normal. But if I take one log, it's not normal, what do? Take another log. And if 2 logs still not make the observation behave, take 3 log. And that's why later on we'll have all kinds of distribution. You'll see that the distribution function got exponential, exponential of exponential, exponential of exponential of exponential. Why is the distribution look like that? Because if the distribution look like that, exponential of exponential of exponential, that means the data when you take log, 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 it will linearize it, make it looks easy to evaluate. Okay, so let's talk about our first log normal, how to do that. Okay, and here, let me just assume you done your exercise, you learn how to normalize something. So let's just say that I start with a bunch of random number. Okay, as usual, I have random number. Okay, and we're gonna do our log normal. Okay, once you have your random number, and then next you'll say that, okay, I would like to consider that log number is my normal distribution number. So when you have your normal distribution, you just say, have a normal distribution of that random number. So you will say norm inverse, okay? And when you have the inverse, you have a probability. And after that probability, you need to have a mean value and a standard deviation. Let's just say mean equal to, give me a mean value, 3. Standard deviation, let me have a, no, 3 is too, no, mean is too close to 0. I don't like it right now. 30. Standard deviation, 5. Okay? So if I do this, okay, and you say, hey, does this look normal? So give me a data analysis histogram from here to here. Okay, and you look at it, most likely you have your bell shape, right? But this time you didn't do the bell shape through your normal way. You did it by just using the normal inverse function. Next step, okay, if I have a normal distribution function, I would like to take exponential with a, let's just say m equal to 500. Okay, let me generate my log normal distribution. Okay, so how to generate my log normal variable is basically just take the exponential of my normal. Now, remember, originally it looks like a bell shape, right? But now if I take the exponential, what will happen? Something big become even bigger, okay? So all I need to do now is just I'll add 300 to this. Oh, a lot of time you'll see me add a very, oh, I'm sorry, not add it there, add it inside. Okay, look at our cheat sheet. Normal plus M. Normal inverse plus M. It did it outside. Why? Let me think. I'll tell you why I added M first, mathematically. Remember, log, if you have a value less than 1, it will become negative. And then things will look ugly. So I'm basically trying to say that, hey, get me out of the trouble zone. Let me follow what I did before. Okay. Yeah, I was right. Okay. Now, let's look at this histogram. Okay, so now we have a first reliability widely used other than exponential bill. Let's just have data analysis, histogram. At this time, from here to here. And, whoa. That's way too big. Let's go back to 1. Okay. Let me do this. Let me have this value divided by normal inverse, exponential, let me use 3. Okay, let's look at this one. People, the only reason I don't want anything big right now is easy to plot, okay? Later, I'll show you guys how to shift, stay out of 0. But even this one I don't like because I have, here, let me look at the minimum value. I have a couple negative I don't like. Okay, how about this? 5. 3 standard deviation, plus minus, still too close. Let me do 6, and let me do 1. Okay, let's see. That will keep me small, but out of 0. Okay, data analysis, histogram. Go from B. Okay. Because the purpose of this exercise is to help you visualize how the transfer going from one situation to another situation. So I want you to visualize that part first. I don't want to struggle too much between. Okay, so people first look at a normal distribution. Now it's using 6-1, okay? And when I draw the histogram, obviously I'm staying, at the center. I'm staying out of 0 and in this area, okay? Now let's look at our normal distribution, a log normal distribution function look like. So data analysis, histogram, and this time from C to C. Okay, looks much better. So now insert data analysis. No, not data analysis. Insert plot. Okay. So this is my log normal distribution looks like. Okay. Ugly? Not too bad. And of course, somebody help me. If we want to do approximation of PDF, how to do that? Take the percentage for PDF, right? And then all we need to do is just, I think, equal to this guy minus 10,000. Okay. And CDF equal to what? Start from 0. Grow by this number. So grow at the end should be very, very close to 1. Yeah, okay? So I'm not going to plot it. We're doing the same old stuff again. Okay? That's not what I want. But so far, you guys see how normal and log normal look like? The log normal data is from exponential. So based on the definitions, okay, how can we get back to our original normalize? So we need to normalize this. Normalize. Okay, so how to normalize this? This guy, you add 300, hey, minus 300. And this guy, originally take the exponential, now give me my exponential back, you linearize it, take the log. So if you take the log, okay, you return back to normal. See that? So what we're trying to say here is that if you have a function, you have a set of observation, once you take the log, it becomes normal. It's called normal distribution. And if, on the other hand, if you have a set of normal distribution data, you take the exponential, it becomes log normal distribution. Everybody with me on this? Okay? And so the lecture note actually also show you that if you want to find the height of the distribution, the PDF, you use this value. CDF, you use this value. Next, we're going to talk about Weibull distribution. The Weibull distribution, all you need to remember is this, okay? If, people, look here. If I let lambda, I let alpha equal to 0, k equal to 1, okay? This whole thing become what? I'm sorry, lambda also equal to 1. 1 divided by minus 1 is 1. X minus alpha. Alpha is 0 is x. K minus 1 is what? 1 minus 1 is 0. So the whole thing become exponential of x negative x, right? So what function? Your CDF is 1 minus negative x, exponential. So exponential distribution is a special case of Weibull distribution, okay? But if you don't have the value like that, you're using any value that center alpha is not 0, is a mean value somewhere else. And then your scale, lambda is not 0. You have a large scale, small scale. And then finally, there's a k function. Usually the k power, they call it k function, they call it the shape function. So k, if it's greater than 1, that means this exponential, this power things grow faster and faster. And if it's less than 1, it goes slower and slower. So the entire Weibull distribution is just a bunch of strange-looking Weibull distribution. So just go Wikipedia, look at here, okay? Here's the PDF and CDF. You can have different alpha and if different k. First thing first, people look at k equal to 1, okay? When k equal to 1, okay, lambda equal to 1, that's your normal distribution. I'm sorry, that's your exponential distribution. But when the k value increase and increase, okay, when k value increase, what did you guys see? The whole thing shifts from, extreme gradually toward the center. Okay, you see the peak is from almost 0 to pink to green. Okay, and guess what will happen if I keep increasing k to more and more value? This thing's gonna move and towards this side. Okay, so since you can have from left skew to center skew to right skew, you can have every possible way of skewing this distribution. That's why Weibull distribution, sometimes the nickname, okay? Please remember that. The nickname of Weibull is shape distribution, okay? And why this is important, when I work for an insurance company, a lot of time I have data, limited number of data. And later when I work, become a professor, guiding grad student doing their thesis, and sometimes they show me their data, okay? Whenever they have a lot of data, they don't know, oh, what distribution should I use? Guess what will be my recommendation? Weibull, because it's shape distribution. When you have limited number of data, you really cannot model in too much detail. But this thing's basically, hey, I don't care. Your left skew data, right skew data, center data, Weibull will be my aspirin or panacea for all kinds of phenomena I'm trying to model. Okay, so Weibull is my #1 choice, and there's a reason for that. It's because it's a shape distribution, and I think here is the example I would like to show you. I'll save as law normal. Okay, and for the shape distribution, here is the way how I do it, okay? So if I have my f equal to, if I have a time, this increment, and then I take the f and give me a distribution look like this, okay? I can even add more x minus alpha here and beta as a denominator, okay? Or you need to care here is that plug in different values. So give me a different value. Okay, so for example, alpha now is equal to 1, right? Right? Let me make it a little higher, okay? Alpha equal to 1, look like that, okay? And if I want these things die quick, okay, alpha equal to 0.7. Oops. Shape distribution. Okay, let me equal to 2. Okay, equal to 3, 1.5. I need to change the scale. Like, can I see the value here? So people, I guess I will use the example here. You have a f function, and you have a 1 minus k function. Just plug in, and the x is just increase or decrease. But basically, you can change the shape by changing the distribution here, by changing the value of your k, or your parameter. Okay? Next. Logistic distribution, yeah? Mine? Oh, I fail. And you want me to demonstrate how I fail. Okay, let's do, so you want me to do it? Oh, fine, I'll do it. Let's just, here. Sorry. Okay. Stop. Okay. Let's redo this. This time I'm using his value and his notation. Oh, here we go. Why? I want to keep half of. Here we go. Why do that? Better. Okay. So let's just use his notation. Okay. 1 minus. He's using. I don't know what is our value here. Okay, 1 minus. Let's have lambda equal to. We'll follow that. Lambda equal to 1, and k. K equal to, let's use 0.5, like what he did, okay? And then the t value, or the x value, basically is time series from 0 to 2.5. So I think I'll add 0.1. Okay, so we're so far so good, right? And then what is my my FT? My FT equal to CDF equal to 1 minus exponential negative time divided by lambda. Lambda is B. Oh, okay. now I see. Lambda is divided by lambda is B1 and to the power of B2. Now I see where's my problem. Okay. Huh? CDF 1 minus negative exponential to the inside exponential x divided by lambda to the power of k yes, that looks correct. Why it didn't work? Victoria, you see where I am right now? Okay, so this is the one, right? Huh? Oh, you mean put it inside? I'm not sure. No. Should be outside. Huh? Right? Exponential. I want to say that I'll leave it to you guys as a homework, but I know what I did, I add another parentheses outside. That works? Okay. Now, the inverse function part, I'm going to show it to you in next slide because I don't want to spend too much time just repeating something you can do Wikipedia, plug and play. But the purpose of Weibull, okay, if you guys can agree with me, is that it's just like a exponential function with exponential in there, just with a bunch of negative, minus something divided by something. But once you change the shape parameter and scale parameter, the shape of the function will change shape. And, well, all I'm trying to say here is, okay, you will say that, okay, let me do it. When you guys give me that look, kind of like, you don't believe me, or something. Okay, so let's change k from that to 2 to 5 to 7. Okay, every time you change the functions, the shape parameter here. People, if this is about some infancy failure rate, okay, can anybody tell me which curve, the blue, green, red, pink, which one the infant die young a lot? Just by looking at the Wikipedia. The blue means what? You have a lot of histogram at the very beginning. So you see this curve grow really, really fast, right? But on the other hand, after the infancy death, it slowed down, right? And can you tell me which function so far in there showing that, hey, people live very, very happy. The babies is fine in the first, at the very beginning, but after middle age, then suddenly all the tragedies start happening. Which curve? Green, blue, green. So you see the green one is kind of like nothing, nothing, nothing. Suddenly, boom, something big. Okay, so the original exercise, what I would like you guys to see from Wikipedia or play with the Excel, is to visualize why I said the shape function. The shape means that, hey, if things happen early, happen in the middle age, or happen late. That's the purpose of the exercise, okay? And now, logistic distribution. Logistic distribution is basically look like a normal distribution, except the logistic distribution versus normal. Let me see if I can find a logistic versus normal curve. Well, just take BS normal distribution. Okay, here we go. Generally speaking, logistic and normal looks very, very similar, okay? Except, okay? That's not the one I like. Here we go. Generally speaking, normal distribution is more bell-shaped like. So in other words, is that if I want to say, hey, my opinion is disagree, but gradually neutral and then highly agree. And if that's the normal distribution, the blue curve, okay, what we're trying to say, logistic distribution is a little more robotics or tighten the survey than normal distribution. So in other words, you look at this, okay, means that at the beginning, normal distribution, you already, the blue one, you already see a lot of people kind of, oh yeah, fine, I'll agree with you. The red one, the logistic is kind of like, no, I'm not going to agree with you. I'm going to reserve my opinion, but after a certain point, it's that let go. So you will see that usually, okay, the peak is about the same points. But the grow is, normal grow a little smoother. Logistic tend to be a little reluctant, and then let go. And same things. Normal distribution, after the peak is kind of like, fine, I'll let go. Logistic is, oh, you violate that, I'm going to cut it out. So the kurtosis of logistic distribution is a lot tighter, and then a normal distribution is a lot more spread. And one exercise people do is in a lot of online survey or stuff. And remember, a lot of times they'll ask, are you a robot or you're a real person when you do, when you Google, right? And they also look at the distribution. If you're trying to figure out certain stuff, they usually can speculate, hey, this is from a robotic group. This is from a real human group. What's the comparison based on? If it's robotics, it's more logistic-like. It's very, very sharp. And then the normal one is usually, central limit theorem, easy grow, smoother grow, and smooth. So that's the logistic look like, okay? Next, okay, the function is usually look like this. Let me see if I can find. Let me use logistic distribution and directly use these things. Logistic distribution, here's the part I need you to understand. They're doing the same thing. I don't like. Okay, I will cover this later when I give you the exercise. Okay. Now, the next things I'm going to talk about is about extreme value distributions. Okay, extreme value distribution is even talking about stuff about risk or reliability based on a lot unusual cases. The focus is beyond certain points. So, for example, a lot of dam or bridges, when they design, you know, a bridge will face what? Flood, right? And building will face earthquake, right? So, would you spend $1 billion just to build one dam and to sustain earthquakes that's say 11 scale 10? Why? Way too expensive. So what you need to do is to say that, okay, in this area, how big the earthquake could be, like in Carolina, okay? If you look at the standard, let's just say housing standard for flood or for wind, hurricane, okay? Do you think that the house here for apartment versus the house in the Outer Banks is going to follow the same standard? Because, you know, the hurricane and the insurance company basically say, we're not going to insure you anymore because of the flood insurance is ridiculous. But how do they decide that? Usually they have two different ways to do this for extreme value distribution. Okay, you just have, say, 100 years of flood record, or 100 years of earthquake record. So the 100 years will be up, down, some big, some small, like this, right? And once you decide this, okay, accumulate 100 years of record together, what can you do is you basically said that, okay, if I set up my level at, say 100, say 10 feet high for UNCC, oh, we should sustain 10 feet high. Then basically people will ask you, okay, how many times in the last 100 years? Suppose, I don't even believe we have 100-year record for Charlotte, but let's just say that the last 100 years, okay, how many times the flood is over 10 feet? And the probability is too small, they will say that, okay, so how about after, 8 feet, 6 feet, and then they'll keep dropping it. Every time it dropped means what? The building cost will drop, right? But the probability of exceeding that extreme event will increase. So now you see reliability analysis and risk analysis become a game of negotiation between engineer and the user. I want to build cheap, but if you build cheap, the risks, the flood will be high, will be more. So you can do this in two different ways. One is you using the x-axis basically said that, okay, let me have a distribution, and then let me say that, okay, let me go back to my ugly looking function. It's 2. Okay? There are two different ways we can do this. One is I'm using, so this is the flood, right? Let's just say that 1 feet, 1.5, 1.2. You know that the more you Let me insert a shape. Is there a shape somewhere? Yeah, I want to insert a shape. Under draw. I just want to insert. Okay. Oh, thank you. Okay. So here, what I want to do is something like this. Okay. And shape, fill, and let me gradient. I thought they can have semi-transparent. Couldn't find it. Oh, here we go. So let me do it. Now I got it. 70%. Okay, so for the extreme value distribution, you can talk about this in two different ways. One is you increase the percentile or quantile and say that, oh, I want 80%, I want 70%, I want 60%. Okay, so if you said that, oh, I want to cover, only 0.1% of cases, so you know that you have to increase your X more and more to cover your Y more and more. So you look at the 100 years of data, you basically have a distribution here. You're saying that, hey, how are we going to negotiate this? If engineers start saying this, that, okay, we can build this, that's 2 million. Build this way is 3 million, 4 million. And sooner or later, you say that, okay, to build that high, that strong, I need this much of money. And then they turn around and say that, okay, if we can build that high, what percentage of event you can cover? And the other way is, we want to have this percentage, and then how much, if the, say, National Highway or National FAA come up with a standard for the airport or for the bridge, sooner or later, what will be the case? They will say that, well, if you want to operate under the National Highway Safety Guideline, you have to chip in. Your state, you need to put in this much of money in order to follow the standard. And then, of course, you can turn around and say that, okay, I can build it this much, but you need, in order to follow the standard, the federal need to chip in how much money. So building that largest event known for parent distribution or like flood high or wind speed, really at the end is there are two sides of people argue based on a distribution. Okay? There are three different types of general extreme value distribution, and this is exactly what they call it. Okay? Type 1, type 2, type 3. Type 1 is Gumbo, type 2 is Fritchett, type 3 is reverse Weibull. And look at the general form of the distribution, okay? Exponential of exponential. Inside the exponential is 1 minus k to the x minus a mean value divided by, you normalize the z-score, and you have that proportional with your shape parameter. Okay, k is your shape parameter. Sigma, they call it scale parameter. Basically, is the standard deviation you use, and mean value is the height. Okay, by turning this distribution into k approximate to 0, k less than 0, k greater than 0, you have three family of the distribution. But look at these things, okay? Exponential to the power of something, okay? If that's the way you generate the data, to look at this data, if you can model this data, people throw you a set of data, how you're going to model this kind of distribution. Take log. First time you take log, get rid of this exponential, right? And usually you see why they have a negative exponential in there, so they can avoid to have the very small value. Okay, so they take log again, and so you can also bring the k back. Yeah. Every shape, every distribution is just a transfer function with one exponential, two exponential, three exponential. How you handle the data, take one log, take two log, take three log. So this class, I can tell you, we're going to have at least 1 month or 1.5 months just dealing with a bunch of log. And once you take the log out of that, it looks almost like your DOE class, just x transpose x, x transpose y. It's a bunch of regression we're going to deal with. Except this time we're not dealing with the regression based on the time itself. A lot of times based on the distribution. So we're still doing maximum likelihood, but the game we're playing with is not how things look like. I can tell you in DOE, you can imagine that I have a bunch of coins in my hand. I spread the coins on the table. Then because my hand's throwing those coins on the table, you should see they have a vector. So you can say that, oh, X and Y related based on what? How they scatter, right? That is your experimental design class about. In this class, we're not looking at it, how they scatter. We're looking sideways, how those coins stack together. We're looking at their histogram. Where are you going to have the peak? Where are you going to level off? So this class is still modeled. We're going to have a lot of regression involved. It's called life regression because it's an insurance company, or Cox regression, or proportional hazard regression. And when we deal with those regression, we're not modeling between X and Y how the coin spread. We're modeling how the coin stack into a distribution. And when we say stacking them, you turn them into a percentage. It's a what? It's a histogram, it's a PDF, it's a CDF. Okay? Now, yeah?
So why do we use the generalized value distribution? I know it's for insurance, but
Oh, so in this class, since I'll cover a little bit, but general, the stuff we're going to do is mainly in the gumbo, in the log normal, in the Weibull world. Because what I'm saying is, most of the cases you deal later on, even say your future jobs, is about, hey, when we should schedule to change oil, when we should schedule to have a physical exam for all the high-ranking officer, when is the schedule we need to double check or have a psychological evaluations of our soldiers, our sailors. So all the performance measurement it's based on how late is too late. Before it's too late, we better do something. Extreme value distribution, a lot of time, is more about, okay, how are we going to build this to last for another 100 years? Or, how bad could it be? We'll cover a little bit on the extreme value side, but most of the reliability and survival analysis, even including the COVID cases we're dealing with, usually the distribution you're going to use should be enough using log normal, gumbo, and Weibull distribution.
so this is just for special cases
Right. And the way how I would say is that for undergrad to master level student, even PhD dissertation, most of the data, airline data, a lot of stuff I'm dealing with, I don't need to use Fritchett and those field distribution. Gumbo sometimes a little bit. Okay, I'll show you the case. But what I'm saying is, when you take log, how extreme, how much outlier you're going to see. Very, very unusual cases. So that is, I would say, beyond the scope of I encounter in real world. Okay. There are insurance company of insurance company. Basically, insurance company, they want to make sure that they cover their risk. So they invest in, there's two biggest one. One is two countries dominate this this kind of insurance for insurance. Guess which two countries? Both in Europe. Amsterdam, Dutch, and London. Why? Because in the 19th century, they covered all the sea merchants, and at that time they're still using sailboat, and so they need to buy insurance, and all the insurance companies need to find a way to say, hey, let's share risk together. Or even the company I worked for before, it's called Liberty Mutual. Why is a mutual insurance company? It's because of Boston got a big fire, and after the fire, everybody said that, man, we can not afford to deal with the risk ourselves. Let's share the risk, try to piece things together, okay? But one more extreme distribution I would like to talk about is called Pareto distribution. Pareto distribution, and I'm not gonna give you homework exercise here. I'm just explaining it. Pareto is for income. You guys ever heard Gini index for income? And it's basically said that, let me find a term for you to look at. Okay, it's about Gini index. Okay, it's about distribution of data, of income. Okay, and the equations basically, I can't remember, is the top how many percent cover how much of the overall money. Okay, do you think this country is distributed evenly, or this is not a very balanced country? No, we're not. Okay, but on the other hand, some so-called communist country, for example, China, their one-party system. Do you think their income distribution even out, or they have rich, very rich, poor, very poor? Yeah. So the how to come up with a tax system, and how to have transparent information so all the trade can be transparent. Usually, and the other thing, of course, is education. If you have good education system for all your citizens, then that can balance. But Gini distribution, basically, Pareto distribution is basically trying to model how much extreme value you're going to have for your income. Okay, and finally, this is your homework for today. Okay, I will go through. Do I have time? Okay, good. Okay, so the homework is on this slide. Okay. The homework basically doing the following. Okay. I will call this failure function ft. Okay. Okay? And then let me do this. Okay? If this is ft, the other function is called st. Okay? St equal to the survival function equal to 1 minus ft. So people look at this. Or our failure or our CDF is from 0 to 1, right? Right? The top one is you know is a CDF, is a failure from 0 to 1. When flood getting higher and higher, way longer and longer, sooner or later everybody dies, right? That's the probability. So what is your ST gonna look like? ST gonna ST gonna look like this. Okay, so at the very, very big, yeah. Doesn't matter. Just any CDF right now. You agree with me? All CDF is from 0 to 1. It's a monotonic function. So at the beginning, if ft is 0, st is 100%. So in other words, at the beginning, I have 100 soldiers, I have 100 machines, I have 100 whatever. At time 0, everybody survive. So it's 100%. How many failure? Nada. At the end, all fail, nothing lasts forever, and ST is going to be close to 1, close to 0. Okay, so FT and ST, it looks like that. The second thing is that here is a bunch of functions we learned, distribution we learned so far from Wikipedia. You can find some. Okay, so exponential look like this, right? Lambda. Here, let me make it bigger. Okay. Would you agree with me? This is your exponential function. Okay? So if 1 minus ft, you get your st, right? St is 1 minus, and then take a natural log of what you generate, and then plot them against t. And then you should see that log st and t can be aligned. So let me go back, show you the first one. Okay. Here is, no, I will start from don't do this one. This one's too hard. Let me use this one if I have time. Okay. Weibull distribution look like this. Okay. Can I take a log of 1 minus over ft look like this? And when I take log twice, this becomes a linear function. So basically, I'm trying to plot log t against log this part. That will be a linear function. Let's go back here, one by one. First thing first, can you generate ft versus t given a lambda value. Can you do that for exponential? Can you do that? Plot, find a t from 0 to 100 or 0 to whatever. And then you define a lambda value. Lambda equal to 1, equal to 2, any lambda, a parameter. And then can you plot this one? Can you? Victoria, can you? Huh? Okay. And can you okay. Let me do one for fun. Okay. Again, this time I'm going to do this over here. So I will. Once I have ft, and then I need t, right? And then I would let t, oh, that's not t. T is from 0 equal to this plus 0.5 or this is plus 0.5. Okay. T increasing, no problem, right? Ft lambda equal to whatever value you want to give me. Lambda equal to 2. So equal to 2 times exponential negative 2 times t. I already know I got it wrong. Oh, I cannot start from 0. I have to start from 0 point. Oh, still not right. Exponential lambda. Lambda equal to 2 exponential negative. What did I do wrong? Huh? Where did I get a K value? Oh, no. In this case, no K value. Yeah. I'm actually cheating. I'm using the most simple one, exponential distribution. Yeah. Oh, that's FT. I need to find ft equal to 1 minus, and not this part. Okay, so let's do 0.1. Okay, let's plot this. No, I don't need to plot it. It grew too quick. Smaller. Okay. So now I generate a FT. Okay. Next, if I generate FT, all I need to do is take the log. I will have a ST. And ST equal to 1 minus z. So if I take the log of the st, okay. Okay, and then let me do this. Okay. I don't have enough time to give you this homework. I'll give you a smaller homework today. I want to generate a couple of this so we can see how it works next time. Okay.